This is a lesson on piecewise functions in a course on precalculus. And I'm going to start you with piecewise functions with linear functions. But piecewise functions can be made up of any function, and you can see that in the example here. I have a parabola. A piecewise function is different functions applying to different domains. So admittedly, when I think about this material, there is an emphasis on your ability to identify domains, and there's also an emphasis on your ability to identify different functions on different parts of domains, okay? So function notation for piecewise functions is we're going to use that regular f of x out front, right? A function of x. But we're going to put a bracket here, and that curly bracket is going to identify which constituent functions make up that larger piecewise function. Often you will see just two of them, as you notice in the example over here. But there could be more than that. There could be an infinite number of piecewise functions. It can include any toolkit function. As long as it's a function, it can go into a piecewise function. Remember, transformations apply. Any transformations that apply, we can use that as we're looking at those constituent functions. And we're going to, again, make particular note of domain and range, more so domain, because you can see within this larger function, with each constituent function, it has its own domain. And those domains are not overlapping on the line, right? So if you look at the example that I put up over here, if I have a number line, I have a number less than 4, right? And then I have a number greater than 4, and there's no overlap between those two functions. Where one ends, the other begins, okay? So watch out for that. I wanted to do this example here to kind of give an idea of what's going on with piecewise functions as we're looking at them. And the instructions for this, it says, given the piecewise function, evaluate it for the given values. And what I'm going to note about this example that I chose is I don't like it necessarily, because often when we do these domains, we go from the lowest value of x to the highest value of x. And you can see over with this example is that we have the negative, sort of the going this direction to the left on the number line on the bottom and going to the right on the top. If I were doing this, I would reorder it. And I think it's in this order for this problem in order to make you pay particular attention to those domains. Because what you can see is what we're going to do is just evaluate that function at each value in here, but we need to determine what part of that piecewise function we're evaluating based on the number, right? So if I look at 7 here, I'm going to note that 7 is greater than 4. So I'm going to use the first part of this function. So I'll go 3 times 7 minus 5, that's 21 minus 5, which is 16. So f of 7 is 16. I didn't use the parabolic part of this because it's not within that relevant domain. When I look at 4, well, 4 is kind of interesting here, right? 4 is that middle point where one ends and the other begins. And I want when it equals 4. I'm going to note when the value x equals 4, then I'm going to evaluate the function. And for me, that happens at when x is less than or equal to 4. So we have that equal sign in there. So I get 4 squared, which is also 16. Very interesting. And then negative 3, I can see negative 3 is less than 4, right? Negative 3 is less than or equal to 4. So I'm going to use the second part of the domain. So I'll go negative 3 quantity squared. Remember, you have to do the quantity. If you're plugging this in the calculator, put parentheses around that negative 3, and that will give you a positive 9. If you just go negative 3 squared, it's going to square the 3 and then take the negative of it. So watch out for that. So that's just a basic about piecewise function, if you get the general idea there. There's a few learning objectives I expect you to know for this lesson. The first one is obviously to evaluate it, to be literate with what part of the piecewise function applies for what value, depending on the domain. And another learning objective I have for you is to be able to graph piecewise functions. And I have a couple of these just to get used to them. Here I notice that my piecewise function has 3 different parts. 1, 2, 3. So there's 3 different domains. And I'm going to note that the 3 different domains. There's a domain that's less than -1. And you can see that this one is by convention ordered from lowest to highest for the x values. So the first numerical value for x that I have is -1, and then the next one is 2, and then there's something greater than 2. So I have 3 different pieces on my domain that have a different function each. All right. So when I'm drawing this, I'm just going to go downward. The first function I have is just 3. Y equals 3. So I'm just going to draw from -infinity all the way up to positive or -1 there. I'm going to note the equal sign here, that I need a solid dot where it ends at -1. And I'm going to put an arrow here. I think when you do stuff in Desmos, when you get used to graphing lines in electronics using technology, there's not an arrow on that, but we're going to make note that it goes all the way in that direction, right? For any x less than or equal to -1, the value is going to be 3. The second portion here is a line. It goes over the y-axis, so I'll be able to use this intercept. So it has an intercept at +1, so I know to put a point in there, and then I'm going to do it the easy way. The slope is rise over run, so that means if I go down 2, I'm going to go over 1, right? Down -2 over +1, that gives me a slope. So, and that is true from -1, so I'll connect those 2 points, all the way down to 2. So there's to 1, and then there's to 2. And when I look at this, there's an open dot for this function at -1, and there's a closed dot at 2 where this function ends on the upper part of that domain. For any x greater than 2, let's put that on there, the function is 0. So I'm going to go like this, get my line as straight as possible, and put an arrow on it. So it's right on that x-axis, greater than 2. I'm going to put an open dot here because it has no equal sign right there. Okay, so that's a simple, just can you graph a piecewise function? Let's do a harder one. I think a harder one, that may be easier. There's just a couple of flat lines, and then the line you're given, you can use the x-intercept. But when you're given a more complicated example, and you can see again, we have 3 different functions here over 3 different domains. We have -4 being a location, a limited domain, and then 2 also denotes a different domain for these 3 different functions. It says sketch the graph of this. So I'm going to go from left to right, part A, part B, and part C here. Part A, I'll do in blue, 1.5x plus 7. Well, it'd be really nice if I could graph like I did on the previous, where I have a x-intercept and then I can just do my line. But that's not what we have here, unfortunately. Unfortunately, we can't do that. What I'm going to note is that I could plug in some values near. For example, I can plug in -4, and then I would get a value, and I could just plot that. I can also put in maybe -5, since it's right here. I can put in -5 and evaluate that and be able to have a point along there. So overall, what I'm going to do is I'm going to plug in some values, and this is a standard way to graph, right? For each value of x, I'm going to get an output f of x, right? Or an output y, and I can just graph those points. So I said I wanted to do -5, -4. It seems like I need to be able to do 2. Let's evaluate 2, and then let's evaluate something bigger than 2. Let's go 5 again, right? That's the other end of my graph. So when I evaluate those, I'm just going to put in that value like I did on the example slide where I first introduced piecewise functions, and just evaluate them at each point with the correct function, right? So if I have negative 5, 1.5 times negative 5 plus 7, negative 5 times 1.5 is 7.5. So I think overall I get a negative 1/2 there for that one. At negative 4, I can see that my function is still the first part of the piecewise function. So I have 1.5 times negative 4 plus 7. I was thinking 6 because 1.5 times 4 is 6. So I get negative 6 plus 7. That's 1. When I move to part B, then it just goes to 3. For any number between negative 4 and 2, the value is 3. All right, so I can just put that in there to be honest. So here is the middle part, 3, done with that part. When I get to 2, I'm going to notice that 2, I have a different value. It needs to start down here with an open dot. So I'm going to have to go negative 0.5 times 2 plus 5. Well, that is negative 1 plus 5. That's a value of 4. And then I'm going to do that again for my last point on my graph to be able to figure out where it leaves the graph over there. And I get, what is that, negative 2.5 plus 5, so that's a positive 2.5. So I'm just going to plot those points and fill in the dots here. Negative 5 is negative 0.5, so there's that point. 4 is 1. So in between those two, that's what it's going to look like. It's just a line that connects those two. It has a positive slope. If I extended it up this way, it would have an intercept of 7, but that's not relevant for a piecewise function. I only want that line from here to negative infinity. In between, I already drew 3. I guess I'll put ends on it. It can't equal here, and it is a closed dot over on this end. And then with the third part of this function, 2 is 4. We already have that. Oh, no, we don't. We need to put 2, 4. So it starts up there, and it can't equal that. And it can, I'm just putting a dot there. It's going to keep going off the graph. You can see it keeps going off the graph. Okay. And I think I could draw that a little bit better. There we go. It keeps going off the graph. So that would be the graph of this piecewise function, is I just evaluate points from one domain to another, and that will give me the piecewise function. Another learning objective I have for you this lesson is for you to be able to write piecewise functions given the graph. And I've found in my experience that this can be a little bit more challenging for students. And mostly because what they like to do is, on the previous slide, we had a line end in the middle, and some students just like to guess like what the x-intercept is, or they get kind of confused, like how do I find the equation of the line if I don't have all of the line, right? And so what we can see for this function is there's two different parts. There's a portion less than negative 5 and a portion greater than negative 5 on the domain, right? That's what this is saying here. And we need to figure out what are those two expressions for those pieces of that piecewise function. So let's do the smaller portion here, the top part of this line here. What I'm going to notice is they're both lines. So I know they're going to have the form y equals mx plus b. Okay, so I'm going to let there be a b1 and a b2. I'm going to solve for those, and I'm just going to fill in the mx plus b for each one of those lines. So the first thing I'll do is figure out the slope, and given the graph, I'm just going to do rise over run. And what I notice is that for every negative 2 in the y direction, I go plus 1 in the x direction. So that makes the slope for the first line, g, the top part of this graph, 2, and then I'll fill in the rest of this. Negative 2x plus b1. I'm just calling it b1 because it's the first part of the function. I'm going to do the similar sort of thing for h down here. I'm going to notice the same thing. If I go down 2, right, if I have a rise of negative 2, I'm going to have a run of plus 1. So my slope for the second line is actually the same, negative 2. It has a different intercept on the y-axis, but they both have the same slope, and I don't know if I can kind of tell that they're parallel on that graph. I don't know if I would have guessed that, but that's what's true. The other thing I'm going to do for this, in order to figure out those y-intercepts, you could guess them. But remember, what I want you to do is you need to be able to algebraically solve for this and prove to me that you know how to find the y-intercept, not just like eyeball and guess on a graph, okay? So what we're going to do, of course, in order to find the intercepts, what we can do is plug in a point that we know. So I know some points here. I know -5, 4 for the g of x is a point on that line. And I also know that -5, -2 is a point on the other line. So I can use those inputs and outputs in order to find my y-intercepts. So for g, I can say that 4 equals -2 times -5 plus b1. And so when I solve here, I get 4 equals 10 plus b1, so b1 has to equal -6. And you might be able to, like I said, guess this as you project a line down here. We're going to get down to -6. So when I write that equation in my box, overall, I'll put -2x minus 6. Done. For the first part. We're going to do the same thing for the second part here. So -2 equals -2 times -5 plus b2. -2 equals 10 plus b2, and so b2 equals -12. So I can fill out the rest of that equation. I'll write in here -2x minus 12. Okay, so this work on the side here, I want to see that in your algebraic work. If you're turning this into me, I want to see that. The last learning objective I have for this lesson is to do a piecewise function in application. All right, can you read a word problem and recognize that this is a piecewise function? A function applies for a certain domain, and then another function applies for another domain. So this is a summer job. You have a summer job. I have a summer job. Maybe you don't have a summer job, so good for you. Let's pretend you have a summer job that pays double for overtime, working more than 32 hours a week. After 32 hours, you earn 2 times your regularly hourly rate of $9 per hour. Okay, so do you see the two different domains going on here? We have what you get paid for 32 hours or less working in a week, and we have what you get paid for 32 hours or more working in a week. And I'm going to define my variable here. It may have you use x, but I like using t for time. You could use h for hours. That would work too. So I'm just going to say t is number of hours worked in the week, right? Number of hours worked per week. And when I think about what's going on here is I have an f of t, and there's two different parts of it. I'm going to have some function, some first function and some second function. And like I said, the second function is going to apply when t is greater than 32 hours. Up to 32 hours, I'm going to get the first rate, but anything over 32 hours, I get the second rate. So that means I need to figure out the domain for the first part of this function. And what I'm going to remind you, because we're working with a word problem with real numbers, right? You cannot work negative numbers number of hours in a week. So we're going to have to start this at 0 and then take our time all the way up to and equal 32 hours. Okay, so those are the domains that we're working with. I think those might be easy to figure out. We need to figure out F1 and F2. What's the, how do we figure out your paycheck with those two different functions? So when I think about F1 is the rate you're going to get for less than 32 hours, which they said is $9 per hour. F2, I think, is a little bit more difficult here. This function has to encapsulate what you earned less than 32 hours as well as what you add on with your overtime. So this is like the dollar that you'll get on your paycheck, right? If you work less than 32 hours, you'll get this amount on the paycheck. But if you work more than 32 hours, this has to include all the way up into 32 hours and that double time amount. So what I'm going to note is that up until 32 hours, you're going to get $9 per hour. So there's this base rate that you're going to get. And then after 32 hours, you're going to get double that, which is 18, right? You earn 2 times your regular hourly rate. So 9 times 2 is 18 per hour. And then you're going to take the total hours you work and subtract 32, because that hourly rate for double time is only applied to the hours over 32. So that's why I need a t minus 32 in there. Okay, so when you're writing out this function, you can put that in there. So I'm going to erase this in here and put in my different constituent functions. This is 9t, and this is 9 times 32, whatever that is, plus 18 times t minus 32. Okay, so that is your answer where it asks for the piecewise function. 2 more questions for this. It says, how much money do you make if you work 30 hours? How much money do you make if you work 34 hours? So we're going to notice that we're in the 2 different domains. 30 is less than 32, less than or equal to 32, whereas 34 is greater than 32. So for part B, I'm just going to use this. Part B, my pay is going to be $9 per hour times 30 hours, which is $270. Part C down here, I'm going to use the second part of the equation for part C. So I'm going to take 9 times 32, whatever that is, 9 times 32. What is that? 288. And then add on 18 times 34 minus 32, which is 18 times 2, which is 36. So when you run this number through your calculator, what do you get? Must be $324. So that's how you would work through that word problem. And I found students, again, find it a little tricky. Different parts of this problem that students find tricky is sometimes they'll forget to add on that original amount up to 32 hours. And I often see them miss this lower value of 0. Like you can't work less than 0 hours per week. So you have to include that on your lower bounds. Otherwise, it's not too bad. I think it's a nice exemplification, straightforward exemplification of piecewise functions.